This conference will now be recorded.
Hello everyone. Last class, polyhalogen compounds, that was the last topic and it was still continued. Trichloromethane, which is also known as chloroform, we have already started that. We'll finish it today. Then some more polyhalogen compounds and their application. We'll also see some related problems, and after that we'll also discuss Freons, that is the chlorofluorocarbons. So chloroform, its physical properties, if we consider, they are liquid obviously and also colorless. There is no such specific color. It is just like, looks like water. But there is a peculiar sickly smell and also burning taste. Now vapor of this molecule, if it is accidentally inhaled, there will be unconsciousness feeling because it depresses the central nervous system. Once it was used as general anesthetic, though nowadays it is not used, but once it was used. Fine. Nowadays it is replaced by less toxic and more safe anesthetics. Chemical properties, what kind of reaction it can give? Oxidation reaction, it can undergo oxidation in the presence of light and air, light induced reaction. And when we are saying air, that means it is basically supplying oxygen to form phosgene, which is also known as carbonyl chloride, COCl2. Now this molecule, that is the product which is obtained by oxidation of chloroform, this is very poisonous, and that is the reason its presence makes chloroform unfit for use as anesthetics. Because if it is stored for a long time and if it is stored in normal bottle, suppose if it is not stored in dark bottle, then what will happen? There will be effect of light and air. Though it is tightly closed, but still it is not leak proof bottle. Then what will happen? There will be presence of oxygen and also light, and as a result this reaction will be producing the poisonous compound, which is carbonyl chloride. And this is the reason that nowadays it is not used, because if by chance this product which is obtained in presence of light and air, its amount, it is crossing some certain level, it will be harmful for us. So that is the reason that nowadays it is not used, and it is replaced by less toxic, safer anesthetics. So the reaction you can see here, two molecules of chloroform, reaction with oxygen in presence of light, there is formation of COCl2, phosgene. This is known as phosgene. The structure will be like this. ACl is the byproduct. So this is oxidation reaction of chloroform. After that, reduction reaction of chloroform. It can undergo reduction with zinc and ACl. So these two are the reducing agent that we are using here in presence of ethyl alcohol as solvent to form methylene chloride. So chloroform we have taken here 2H, then Zn and ACl. In that is, this H is basically coming from ethyl alcohol, and what we are getting, see, CaCl3, which is basically carbon attached to 1 hydrogen and 3 chlorine. Now it is attached to 2 hydrogen, 2 chlorine. So it is converted to methylene chloride. So this is the reduction product, because here CCl bond is replaced by CH bond. Fine. Next, nitration reaction of chloroform. It reacts with nitric acid to form chloropicrin. Now chloropicrin is basically this molecule, NO2.CCl3. It is also known as trichloronitromethane. Methane derivative, obviously this molecule. Methane is CH4. Now if 3 CH bonds are replaced with chlorine and 1 H, that will be replaced by NO2, then you will be getting the structure of chloropicrin. The name is trichloronitromethane. In presence of HNO3, which is written here in this way, HNO3, you can also write it HONO2, concentrated condition, there is formation of this molecule. So as if here this OH bond, that is, sorry, this CH bond, as if it is replaced by CNO2 bond, because Cl3 it is still there. Okay. So this H and this HO, now together it will make water, which is the byproduct. Fine. fourth reaction, carbylamine reaction. Now this test we use for detection of primary amine, because for this reaction one of the reagent is primary amine must be present. This is the general form RNH2. So C CH2NH2, or R group is CH2. So for this reaction you can take any primary amine, and you also have to take, that is a reagent that must be there, which is mixture of chloroform and potassium hydroxide, alcoholic potassium hydroxide. Chloroform reacts with aliphatic or aromatic primary amine, because this R group, it may be pH also, or any substituted pH. So aromatic primary amine you can take normal aliphatic primary amine, both will be fine. And alcoholic caustic potash, that is KOH, and you will get the formation of RNC, carbylamine, and it is having a very foul smell. And because of this specific smell, this reaction can be used for identification of primary amine, because whenever you are doing any identification reaction, there must be some visible color change or precipitation, or some specific colored gas production, or foul smelling gas production. Not foul smelling, but any specific smell should be there. So in this case you can see it has some specific smell. So whatever carbylamine is produced, because it depends on what kind of R group you have taken, but any type of carbylamine, whether this R is methyl or PH or ethyl, always this molecule, there will be some foul smell. So that is why this test can be used for identification test of primary NH2. Okay, but here one of the reagent is chloroform, so that is why we are discussing this reaction under the chemical properties of chloroform. So here chloroform you have taken, you have added some 1 degree primary, that is primary amine, and also you have to add potassium hydroxide, which is caustic potash, and ultimately there will be formation of this foul smelling molecule. These are the byproducts. So when it is CH3NH2, this is the molecule methyl carbylamine. You can also call it methyl isocyanide, because when it is CN group we call it cyano, and when it is NC we call it isocyano. Next reaction is dehalogenation. Now as the name suggests, dehalogenation, that means there must be removal of halogen atoms. We have taken 2 chloroform, both sides of 6 silver atom. Now there is a specific reason why we have written it in this way, because here the CH, you can also write it in this way, HC 3CCl bond, then 6Ag, again the same molecule. Now as if it is removal of 6 chlorine with 6 Ag, so there will be formation of silver chloride precipitate. So this HC and this HC together, it will be now attached, and as a result there is triple bond formation between 2 carbons. So what we are getting? We are getting acetylene by dehalogenation of chloroform. But remember, you have to take 2 chloroform, that is, this must be the mole ratio of silver and chloroform, 6 Ag. That is 2:6, or you can say 1:3. Next reaction, hydrolysis. So obviously you have to use water, but it is aqueous solution of NaOH, that is basic solution hydrolysis. CHCl3. So here if we imagine the structure of chloroform, there are 3 CCl bonds. So all these CCl bond, as if now it is replaced by chlorine OH bond. Okay, but this is not, this is the intermediate, this is not the final product. Finally what will happen, as it here same carbon is containing 3 OH group, right? So one water molecule will be removed, that is H2O, and if water molecule is removed, what is left? HCOOH, right? But as the medium is basic, it will not remain in this acidic form. This is basically formic acid, but it will not remain in this form. Here this H, it will be sodium salt. So that is why final product will be sodium formate. So from chloroform, one molecule of chloroform, you are getting one sodium formate molecule, and if you further acidify it, you can get formic acid. So you can produce formic acid by hydrolysis of chloroform. Okay. Application of this molecule, that is chloroform application, used as an anesthetic, but remember nowadays it is not used because of the presence of phosgene, which is produced from chloroform in presence of light and air. Used in dentistry during root canal procedure, that is basically the anesthetic, that is used as anesthetic. Then in the past it is used as an extraction dissolvable for fats, grease, oils and different items as a laundry spot. Okay, because all these molecules, that is fat, grease, oil, whatever it is, grease is mainly hydrocarbon, oil also there is no hydrocarbon chain, so all these are soluble in chloroform. Okay, so that is why it can be used for as a solvent for these molecules. The major use of chloroform today is in the production of freon refrigerant, which is R22. Now what is freon? This is actually a general term we use. It is mainly used nowadays in air conditioner. And what is this freon, that we are going to discuss in today's class after some time. Okay. Chemically, chloroform is employed as a solvent for fats, alkaloids, iodine and other substances. So if you are doing any organic reaction in laboratory with all these type of substances, then chloroform can be used as solvent. So now it is when it is used as anesthetic but replaced by safe anesthetics, because chloroform in some cases causes cardiac and respiratory failure. Remember, CaCl2 may be present as impurity. It is used as a laboratory reagent for testing primary amines. That is carbonyl test. We have discussed under chemical properties heading of chloroform, where you have seen that how by using primary amine, KOH and chloroform, there is formation of isocyanate, which is having some specific foul smell. So this is used as identification test, and in this identification test, chloroform is also important reagent. Used in the preparation of chloropicrin, chloritone and salicylaldehyde. Now, chloritone is this molecule CCl3, C, 2-methyl group, then OH. So as you can understand, chloroform is CHCl3, right? That means 3 chlorine attached to 1 single carbon. So this part, it will come from chloroform. So when you are trying to make chloritone, that is you are synthesizing chloritone, then chloroform can be used. Then chloropicrin, that structure we have already seen, and salicylaldehyde. Now salicylaldehyde is basically this molecule, that is OH substituted benzaldehyde. Now OH may be at 2 position, that is ortho position, or it may be at 4 position, which is para. This is orthosalicylaldehyde, this is parasalicylaldehyde, and if you want to make this molecule, you have to start from phenol, you have to take chloroform as reagent and basic medium. So for the preparation of salicylaldehyde, chloroform is important reagent. In medicine such as cough syrup, it has its application, and for preservative for some biological specimen. So in biology laboratory, if you see, there is some specimens are kept in chloroform in the jar. So it is basically used as preservative. The next molecule after chloroform as polyhalogen is carbon tetrachloride. So chloroform, what you have seen in the structure, there is 1 CH bond and 3 CCl, but now all the hydrogens of methane are replaced by chlorine. So it is tetrachloride, no hydrogen is there. So it is derivative of methane, but all hydrogens are replaced by chlorine. So now it is CCl4. This is also colorless liquid, just like chloroform. But now the smell is not like chloroform, it is more sweet smell. And if it is present at low levels also, it can be detected by this specific smell. When it is released into the air, it rises to the atmosphere and it can deplete the ozone layer. Now depleting ozone layer, that is not good for us, because when ozone layer is depleted, that is if it is destroyed somehow, then there will be direct UV light coming on us, which is not good, because ozone layer, depletion of ozone layer is believed to increase human exposure to UV rays, and UV rays are not good. Okay, so that is why CCl4, though it has some application, but it should be keep in mind that if it rises to atmosphere, then that is released into the air, then there is a chance of depletion of ozone layer. How we can make CCl4? We are starting from methane as starting material in presence of 4Cl2 and H nu, that is light. All the carbon hydrogen bonds are broken and you are getting CCl4. Another method is you can also start from carbon disulfide. It has same type of structure like carbon dioxide, C double bond H both side. This molecule also in presence of chlorine and anhydrous AlCl3. Here all this carbon sulfur, that is double bond, this side there will be 2 CCl, another side also there will be 2 CCl. So ultimately you are getting CCl4, and total 4 chlorine atoms required. And here we have taken 3 chlorine, that means total 6 Cl is there. So look at the right hand side, 4 chlorine attached to carbon, 2 chlorine that is now attached to sulfur. So we are getting S2Cl2, that is the byproduct. Properties of CCl4. When it is reacting with water in gaseous form, obviously that means we are heating it, steam, not liquid water. Then also we are getting phosgene. Remember, phosgene we also get from chloroform in presence of light and air, that we have just discussed before some time. So here also that is when it is CCl4 and reacting with steam, then there is formation of phosgene and water. Then reduction reaction. When it is reduced in presence of FeHCl, then one CCl bond is converted to CH. So you can also consider this method as if it is synthetic method, or that is preparation method for chloroform, because in this reaction after reduction of CCl4 you are getting chloroform. Now what is its importance? It is used in the manufacturing of refrigerants as a cleaning agent and as fire extinguisher, solvent for oils, fat, resin. This application you have also seen in case of CHCl3. So it is not very uncommon that some of the properties of CCl4, if it is common with CHCl3, that is not very anything unexpected, because it may be so, because after all the molecules are so alike in structure. Only difference is one CCl bond is extra in case of CCl4 compared to CHCl3. So some of the properties may be same. Medically, it is one of the most potent hepatotoxin. Now, what is hepatotoxin? Hepatotoxin is the substance will be called hepatotoxin if it is harmful for liver, toxic to liver. Now, if you are thinking that if it is toxic to liver, then why it is important? Now, the reason is sometimes what happens in scientific research, suppose you want to evaluate some hepatoprotective agent. Now, hepatoprotective agent, it is the opposite word of hepatotoxin. To nullify the effect of hepatotoxin, you have to use hepatoprotective agent. That means any substance which will detoxify the liver. Now, if you want to know the effectivity of this hepatoprotective agent, obviously first you have to use some hepatotoxin, then only the question of nullifying it arises. So that is why here the role of CCl4, that is how it is used. First it is used to toxic the liver so that it can be used to evaluate the effectivity of hepatoprotective agent. So that is the reason it is widely used in scientific research. So these are the applications of CCl4. Next polyhalogen, Triiodomethane. Now mostly you know this molecule by the name Iodoform, and there is a specific name, the specific reaction name also, which is Iodoform reaction, which is one of the type of haloform reaction. Because haloform, when you are saying, this is the general term, halo may be fluorine, chlorine, bromine, iodine, but when the haloform reaction, iodo is the component used, that is iodine is used, then it will be called iodoform. So general, that is the structure of iodoform, which is it sounds similar as chloroform. So in case of chloroform, the formula is CHCl3, and if it is iodoform, it will be CHI3. And if you want to write the structure of haloform general, it should be CHX3, because this is the general structure, haloform. So when it is chloro, it is chloroform. When it is iodine, it is iodoform. Now CHCl3 that today we have discussed, it is colorless liquid, right? But when it is iodoform, see, this is yellow solid. So this is also expected because when you are moving from chlorine to iodine, 3 chlorine replaced by 3 iodine atom, and iodine having more atomic mass. So this molecule, it is having more molar mass compared to CHCl3, and with increase in mass, there is obviously change in physical state from liquid to solid. Preparation method for this molecule. Iodoform is prepared by iodoform reaction. So iodoform reaction is basically used for, it is actually an identification test to check whether CH3CO group, ketomethyl group, is present in the molecule, or this type of group, that is CH3CHOH. So this type of groups, if it is present in the molecule, if we want to confirm, then we do iodoform reaction. That is the application of this reaction. But in this case, we are discussing this reaction for other purpose, and the purpose is now we are synthesizing iodoform. But actual application of this reaction is to check whether this type of groups are present or not. And as it is identification test, there must be some visual change or some smell should be there in the product. So in this case, the visual change is yellow precipitate is formed. And this yellow precipitate is nothing but this iodoform, which you can see in this picture. Compounds containing either CH3CO or CH3CHOH group, you have to take a starting material, and what reagent you are using, basic condition NaOH, and obviously iodine, because after all you are making iodoform. So this is the reagent. General structure is given RCOCH3. What you are getting sodium salt of this molecule, RCO. Basically it is sodium salt of the carboxylic acid, but as the medium is basic, that is NaOH is present in the medium, so obviously carboxylic acid will not remain in the form RCOOH. It will remain in sodium salt form. So that is why it is written in this way. But actual product is carboxylic acid that you are getting from RCOCH2. So this is the kind of oxidation reaction. Okay, and this carbon, it is now removed in the form of CHI3. So from left hand side RCO, you are getting RCO minus carboxylic ion, and from the right hand side part, that is the methyl, you are getting CHI3, which is having yellow colored precipitate. And if you have taken this molecule RCHOH CH3, this is also giving you same molecule. Here also precipitate. So this is the synthetic method. Physical properties. Yellow crystalline solid, melting point 121 degrees centigrade. It has a distinct and unpleasant odor. Insoluble in water. That means if we are doing this reaction in water, we can easily, that is why we are getting the precipitate. Because if you are doing the reaction in water and you are getting precipitate, what it means? That product is not soluble in water. That is why it is getting precipitated, right? So as it is not soluble in water, we can get precipitate. But remember, it is soluble in solvents like ethanol, chloroform, which is it's as if the same type of compound, and also it is soluble in ether. Application. When it comes in contact with organic matter, decomposes easily and it produces free iodine, which is antiseptic. Due to its objectionable smell, it has been replaced by other formulations that are containing iodine. So from the first point, you can understand that it can be used as antiseptic. So suppose you need some antiseptic, you are using iodoform on the skin. So when it is coming with organic matter, it will be decomposing and iodine will be produced, because iodine is the actual compound that you want as antiseptic, but we are using it in the form of iodoform. But because of its smell problem, nowadays it is replaced by some other formulations which will also produce iodine. Chemical properties of this molecule. Iodoform has chemical behavior that is nearly identical to chloroform, and that is expected because of their same type of structure. Only difference is, compared to iodoform, this molecule is less stable. Okay, so CHI3 in presence of potassium hydroxide, that is hydrolysis, there is formation of potassium salt of formic acid. Now this type of reaction you have also seen in case of CHCl3. You can also go back to that slide so that you can compare these two. Then reduction with red phosphorus HI, we are getting methylene chloride. Then heating with silver powder, we are getting acetylene. Now this type of reaction also we have already seen in case of chloroform, right? Carbylamine reaction. Now carbylamine reaction, mostly we use chloroform, but it can also be obtained from CHCl3. Then heating, if you are simply heating this molecule, what will be produced? 4 CHI3 plus 3 oxygen. It is producing 4 CO and 6 iodine and 2 H2O. That means from CHI3, when you are heating it, it is reacting with oxygen. There is formation of carbon monoxide, 6 iodine and water molecule. Reaction with AgNO3, there will be yellow precipitate of AgI. So AgI means what? It can act as a source of Ag plus, and I'm saying that AgNO3 you are using with CHI3. That means Ag plus ion is there. So this Ag plus, it can react with I minus, and there will be formation of silver iodide precipitate. But this reaction we cannot get from chloroform, because when it is chloroform, Cl minus is not generated, because CHI3 and CHCl3, if you compare, AgI precipitate you can get only if there is presence of halide ion. There must be presence. In case of CHI3, its covalent nature compared to CHCl3 is less. So that is why I minus can be generated. But when it is chloroform, because of its covalent nature, Cl minus is not generated. So AgCl precipitate is not possible. So this is why this reaction is not given by chloroform. Just ignore this one. Hydrolysis undergoes hydrolysis with KOH when heated with, remember it is alcoholic KOH, yielding formic acid, but as the medium is KOH, it will be potassium salt of formic acid. Next we have reduction reaction. Heating, it decomposes into iodine vapor, and also carbon monoxide is produced. Now if it is kept, that is in contact with air, moisture or light, which is common if you are keeping it open air, right? So if it is kept it like this open for a long time, then gradually it will be decomposed to carbon monoxide and iodine molecule, that is iodine vapor will be produced. Carbylamine reaction, isocyanide is produced, so same as you have seen in case of chloroform. So this is common for both of them, and reaction with AgNO3. So there is formation of yellow colored AgI. And this silver nitrate, it is basically alcoholic silver nitrate. Iodoform can be prepared from all except which molecule? That means there, out of these 4, there will be one molecule from which you cannot make CHI3. Now remember, in the preparation method, what we have seen, that is in the preparation method of CHI3, we have used iodoform reaction. So for that, what we have seen in the first box, preparation method, there must be compound containing CH3CO ketomethyl group or CH3CHOH group. If these groups are not present, iodoform reaction is not possible. So you have to check in this particular reaction question whether in these molecules there is presence of ketomethyl group or CH3CHOH group present or not. And for that, what you will do, you have to write the structure of all this. The first one, isopropyl alcohol. Isopropyl is this molecule, Me2CH. Now, as you can see, here ketomethyl group is not present, that is CH3CO group is not present, but here CH3CHOH group is present because we have H here, right? That means because of presence of this part, here iodoform reaction is possible. But we have to find that molecule from which iodoform cannot be prepared. So this is not correct option. The next option, 3-methyl-2-butanone. Now as it is but, first what we'll do, simply write 4 carbon chain. And if it is 1, 2, 3, 4, 3 position there is methyl group and 2 position on. So this molecule there is presence of CH3CO. So because of this presence of CH3CO, this molecule can also give iodoform. Now compound C, that is isobutyl alcohol. This is isopropyl. So there is 3 carbon, but isobutyl will be 3 carbon, then 1 more carbon, and then OH. Now in this molecule, you do not have any CH3CHOH, right? And CH3CO. So this will be the correct option. It will not give iodoform. But if it is single choice, that means last molecule will also give. And if you draw the structure of last one, it is ethyl one side, methyl one side, and then keto. So here also you have ketomethyl group. So this will give iodoform. So option C, correct option. The major organic compound formed by the reaction of 1,1,1-trichloroethane with silver powder. So you are doing a reaction in which you have taken silver powder, that is simply silver, and this molecule. Now what is the structure of this molecule? 1,1,1-trichloroethane. Now ethane, when we are saying, that means it must be 2 carbon and 1, 1, 1. So if this is 1, another carbon is 2. So the first carbon, there will be 3 chlorine. So that is why it is trichloro. And to satisfy the valency, simply put hydrogen. So in this way, you can draw the structure of 1,1,1-trichloroethane. You are treating it with silver powder, right? Now, remember the reaction which we have seen in case of chloroform and also in case of iodoform. 2 molecules of chloroform or iodoform reacting with 6 Ag. So this is also same reaction, though you can say that this molecule is not iodoform or chloroform, but remember this unit is common with iodoform or chloroform, that is same kind, right? So that is why here same kind of reaction will be there. So see, same molecule written, and this is one molecule left hand side, this is another molecule right hand side. Same type of reaction you have also seen in case of chloroform. Only difference is now in place of H you have methyl, otherwise there is no such difference. So when you have taken chloroform, 2 molecules and there is in between we have written Ag, what molecule you have obtained? You have obtained AC triple bond CH. But in this question, these 2 H are actually methyl. That is the only difference. So now also you will be getting CC triple bond, but this is not acetylene. This is acetylene, 2 carbon, but now it is 2 butane because total number of carbon 4. And at 2 position there is triple bond. So that is why it is 2 butane and option A will be correct. And this 6 chlorine atom together with Ag, it will make AgCl precipitate. So correct option is 2 butane. Be very careful. 2 butane is also written, but It is not CC double bond. So 2-butene is not correct. Ethene is also AC double, ethene is ethylene, simple. H2 double bond CH2. But this is not correct. Acetylene is also not correct. Acetylene will be correct if starting material is chloroform. But your starting material is not chloroform. So first option is correct. This problem is multiple correct choice. So more than one option will be correct. The question saying chloroform doesn't give white PPT with AgNO3. But this type of PPT, if you have taken CHI3, PPT is possible and the PPT is AgI. But in this case, it is not possible. And what is the reason behind that you have to find, and there may be more than one reason. Maybe it is not necessary. The first option is saying it is covalent compound. Now this is actually true, because if you want to get AgCl precipitate, suppose you want to get AgCl precipitate, so for that there must be free Ag plus ion, Cl minus ion, and if you get Cl minus in free condition, that means from the source from which it is coming, that must be ionic. Just take the example of sodium chloride. It remains as Na plus Cl minus. So that is why in sodium chloride solution, if you pour AgNO3, easily you will get AgCl precipitate. But if the compound is covalent in nature, then it is not possible. So option is correct. Then it does not give Cl minus ions in solution. Now this is also correct. Actually, covalent, as it is compound, this is covalent compound, that is why it is not giving Cl minus. So B is as if the result of A, right? It is not dissociated in water. Now not dissociated means free Cl minus ions you are not getting, and that means it is true. And the last option is none of these. But once you know that first option is correct, obviously none of this is not possible, because none of this, if it is correct, that means A, B, C all will be wrong. So these three are the correct options, A, B, C. So polyhalogen compounds are done. Next topic is freons. They are also known as chlorofluorocarbon. As the name suggests, chlorofluorocarbon, that means there will be presence of chlorine atom, fluorine atom, and also carbon. So these three atoms must be present. Chlorofluorocarbon compounds of methane and ethane are collectively known as freons. That means simply consider the structure of methane, CH4, ethane is C2H6. Now you can replace different CH bond with chlorine and fluorine. So different permutation combination possible. So keeping these two compound as source, as if they are the parent, you can consider different derivative by replacing hydrogens with chlorine or fluorine. So all these possibilities or varieties that you are getting from CH4 and C2H6, collectively they are called freons. Extremely stable molecules they are, that means unreactive, non-toxic, non-corrosive, easily liquefiable gases. So these are their properties. Here one picture you can see, which is derivative of CH4, 2 CH bond replaced by 2 chlorine, another 2 CH bond replaced by 2 fluorine. As the size of chlorine is greater than fluorine, so that is why these are the largest sphere compared to this blue one. Freon 12, which is also known as R12, it is basically CCl2F2, that is this molecule in the right hand side. It is one of the most common representative of these groups, and it is manufactured from CCl4. That is, starting from CCl4, you can make this molecule by Schwartz reaction. These are usually produced for aerosol propellant, refrigeration, air conditioning purposes. Most freons, because some freons are used in refrigeration for reducing temperature, so most freons, even which are used in refrigeration, eventually makes its way into the atmosphere. That is, they can be leaked into the atmosphere, where it diffuses unchanged into the stratosphere. And the stratosphere, freon is able to initiate radical chain reaction which depletes O3. So this is a problem with this type of molecules. If somehow they are in atmosphere, ultimately they can reach towards stratosphere where ozone layer is present. And though we have mentioned in the second point that they are extremely stable, unreactive, but remember, when they are in stratosphere, obviously there is high energy. In presence of UV ray is there, so in presence of those light, easily now they can be reactive because high energy condition is there. Now as it can deplete O3, so this is one of the disadvantage of this molecule. So see here we have taken chlorofluorocarbon, which is this molecule. Here 1 CF bond and 3 chlorine bond. This is also freon. It is that is one of the CCl bond is broken, so there will be chlorine dot generation, and also there will be another dot on carbon because it will be radical chain reaction, that is radical formation will be there in presence of UV. So UV releases a chlorine atom, basically chlorine dot. Now this chlorine dot, it is reacting with O3 molecule. Chlorine encounters an ozone molecule. Fine. So what it will do? Now in ozone, one of the OO bond, it is broken, and ClO, this unit is formed. Now further, this oxygen bond can also be broken. There will be formation of oxygen radical. Now this oxygen radical, it is reacting with this ClO, which is already produced in the previous step, and now it is making an oxygen molecule, which is stable molecule, and again Cl dot is there. So free oxygen atom, that is this one is free oxygen atom, it releases chlorine. So this free oxygen atom, it is reacting with another oxygen atom, producing diatomic oxygen, and again the Cl dot is produced. Now this Cl dot, see, it is again, it can again continue the reaction with O3. So that is why it is chain reaction, but it is continuously going on and on. So free chlorine continues to deplete ozone in this way, and that is the disadvantage of this molecules. Next one, DDT. Now this is also a compound where you can see that is, it is example of haloarene as well as haloalkane, because you can see chlorine attached to aliphatic carbon as well as aromatic carbon, and this has some application. So that is why we are discussing this in this chapter. Now this molecule, as you can see, it is known as para-para-prime dichlorodiphenyl trichloroethane. Dichloro D, diphenyl D, trichloroethane. So that is why the name DDT. Now how the name is coming? First of all, if you focus on this part, it is 2 carbon. That means it is ethane derivative. Now in ethane derivative, as if ethane is basically, you can write it CH3CH3, that is C2H6. Now as if this CH3, it is converted to CCl3, and 1 carbon hydrogen bond is still there, another 2 CH bond, as if this is replaced by this para-chlorophenyl group. So that is why this is one para, this is another para, so that is why there is a prime sign, para-para prime, and dichlorodiphenyl. So this unit is coming together, so that is why dichlorodiphenyl, and trichloro, it is because of this, and ultimately it is ethane derivative, so that is why the name is ending with ethane. Okay, how we can make it? Starting from chloral, which is trichloroethanol. Now ethanol, when we are saying, this is basically CH3CHO, acetaldehyde, but if you replace all these hydrogens with chlorine, it will be CCl3CHO, and the name is now trichloroethanol. So you have taken 1 molecule of this and 2 molecules of chlorobenzene, and just write these 3 molecules in this orientation so that you can remove this para hydrogen with respect to chlorine, and also the double carbonyl oxygen of chloral. So as if you are removing water, so there will be carbon-carbon bond formation. So see, this is the new CC bond formed, and this molecule is basically this structure, right? DDT is the first chlorinated organic pesticide. So that is why this molecule is very good example because it is the first chlorinated organic pesticide that has some application. But its problem is the stability and fat solubility. Now, why it is disadvantage? Because suppose if when it is used in pesticide, suppose it is used during in agriculture when plant is growing, and if we are consuming that plant, what will happen? That will be inside on our body, and if it is very stable, so it will remain in our body for a long time, and it also has some fat solubility. That means if it is fat soluble, then also the chance of the storage inside the body, that is also high. So that is why these are the disadvantage. It is prepared from chloral and chlorobenzene in presence of concentrated H2SO4 that you have already seen. And why concentrated H2SO4 used? Because ultimately you are removing water molecule, and concentrated H2SO4 is very good dehydrating agent. DDT is used to control certain insects which carries disease like malaria and yellow fever. It is used in farms to control some agricultural pest also, to kill different insects like housefly, mosquitoes due to its high and specific toxicity. So these are the applications of DDT. So now we are at the end of this chapter, but some problems we will discuss, and this problem will be covering all the topics that we have discussed in this whole chapter. Fine. So in the following reaction, one reaction scheme is given in the question, right? How many carbon atoms are present in X? Now X is that starting material here. What you have done to X? You have done bromination. You have obtained Y. And with Y we have used sodium nitrite and HCl, which is basically the source of HNO2. And this type of reagent, which is source of nitrous acid, when we mainly use it when there is presence of aniline or aniline derivative. Okay, so it means that the molecule Y, there is a chance that it may be some aniline derivative, right? Then you are getting Z. So what happens if you have any aniline or aniline derivative in presence of HNO2? There is formation of diazonium ion. That must be, it means that Z may be diazonium ion. Next stage you are using H3PO2. Now when you use H3PO2 on diazonium ion, what happens? This N2 it is replaced by H. And the final product is already given, the name is given, which is 1,3,5-tribromobenzene. That means it is symmetrical molecule. You have benzene, these are the 1,3,5 position. So at 1,3,5 position, 3 bromine. So this is the structure of final molecule. And what I have said, if you treat diazonium ion with H3PO2, N2 is replaced by H. That means in any of these positions, there may be presence of N2 plus. That means in any of these positions, there may be presence of NH2 also. Because after all, N2 plus is produced from NH2. And the first step you have done bromination. That means it may be that the structure of X, it is some aniline and aniline or aniline derivative. And as you have done bromination, so these 3 positions there is bromine. But it must be simply aniline, because if it is aniline derivative, there must be some other groups. But in the final product, as the name is given, it is clear that other groups are not present. So that is why the starting material, it must be aniline. Now see all the reactions. Starting material aniline in presence of bromine and AlBr3. Basically, this catalyst is also not required because aniline, this NH2 group is so reactive. It is making the benzene ring so electron dense that tribromination, because that is tri substitution, is possible. Then, so whether you use bromine water or in presence of catalyst, always you will get this type of tri substitution. So this is molecule Y. NaNO2 HCl mixture used, you are getting Z. So this is the diazonium ion. Now this is not very stable. Then in presence of H3PO2, this is replaced by H. So this is a final product. So X is it is asking how many carbon atoms are present in X. So once you know X, it is aniline, so obviously total 6 carbons are there. This is an integer type of problem. 1 methyl ethylene oxide treated with excess of hydrogen bromide. You have to find what is the final product. So obviously you have to write the structure of 1 methyl ethylene oxide first. Now ethylene oxide is nothing but epoxide, and this is symmetrical structure. Any of this carbon you can consider as 1. So you can write methyl at any side. It doesn't matter which side you have chosen. So this molecule is treated with HBr. Now as it is HBr, first there will be protonation of oxygen. The lone pair over oxygen, it will attack the hydrogen of HBr. So first there is protonation, because this side there is partial positive charge, this side partial negative charge. Bromine is more electronegative. Oxygen is positive charge. It is carrying positive charge because of this OH bond. Next, Br minus is free in the medium. Now suppose this is carbon number 1, this is carbon number 2, and Br minus is normally when it is acidic condition and you have any substituted epoxide, always Br minus attacks to that carbon which is containing the substituent. Now the reason is, when it is acidic condition, the mechanism it is going through some SN1 type mechanism. So in SN1 type mechanism, what we know, there is formation of carbocation, but as I am saying SN1 type, fully developed positive charge is not there. But even if we are considering partial cleavage of this bond, suppose I am writing is as dotted, if it is partially cleaved, there will be some partial positive charge, and this type of partial positive charge, obviously it is more stabilized by the plus I effect of methyl. But if it is formed in the right hand side, this type of stabilization is not possible. So as it is going through this type of mechanism, Br minus will attack towards the methyl containing carbon. So now you are getting this structure, but as you are using excess of HBr, further another molecule of HBr will be there. Again there is OH group, so oxygen's lone pair can attack this proton. It will be now converted to good leaving group OH2 and Br minus. Now there is no confusion, it will simply attack here, it will be removed. So ultimately, which molecule is the right structure? This is the right structure, right? But here one point I also want to mention. Though we have mentioned it is SN1 type, it should attack only one carbon. But suppose by mistake if you are attacking the other carbon, then what will happen? This is methyl OH. So if somehow it is attacking here, now this bond is broken. Now it will be OH, Br. Now the next step what will be? OH2 will be OH will be converted to OH2 and another Br minus will attack here. And now see what you are getting. You are actually getting the same structure, right? Same as this one. So whatever carbon you choose, you will always end up with the same result. But for extra information, I'm just saying that remember when it is acidic condition, the mechanism is such that Br minus will attack the substituted carbon. So option 4 is correct option, but why the other options are not correct? Because see, in the first option, it is as if that is CC double bond generated. But we are not using any such reagent where CC double bond can be formed. And the second option, here same carbon, that it is actually CH3, CBr2, then CH3. Same carbon is containing 2 bromine, but that is not the product. And the last third option, here only 1 bromine along with CC double bond, but this is also not correct. But one thing is common, as in this molecule total number of carbon is 3, methyl and 2 carbon in the epoxide ring. So see, in all the options, carbon number is 3. So based on that, 3 carbon, right? 3 carbon. 3 carbon. So based on that information, you can't do anything. You have to write the proper mechanism, then only you can find the correct option. Okay. So some more problems we'll discuss in the next class. We'll end the session here because the next problem that is there, it will take some time. So I prefer not to start the question. Thank you for listening. We are ending the session here.